Welcome back. In this chapter, we start by reviewing the main components used in embedded Linux development. We then proceed to a high-level introduction to Yocto and its main components. Additionally, we explain what Docker is and why we're going to use it. So let's get started. The four main software elements of embedded Linux systems are the toolchain, a bootloader, the Linux kernel, and the root file system. When cross-compiling, the architecture of the development machine is different than that of the target platform, which in our case will be the Raspberry Pi. The cross toolchain compiles a collection of sources into these artifacts that can then be flashed and ran on the target platform. Traditionally, most of these elements are made available by the SoC or board manufacturer, and you either have to integrate them manually, especially in commercial projects where licensing and control are important, or rely on automation tools such as LTIB from Freescale, Buildroot, an open source project, the Open Embedded distributions, and Yocto. Yocto actually uses some components from Open Embedded, such as the Open Embedded core layers, and BitBake, a task execution system. Before Yocto appeared, more or less in 2009, there wasn't such an extensive cooperation between organizations as there is with Yocto, and it was usual for each company to sprout their own in-house build system. In a nutshell, Yocto provides a flexible set of templates, tools, and practices which form standards through which embedded developers worldwide can share technologies, software stacks, configurations, and best practices that can be used to create tailored Linux images for embedded and IoT devices, or really anywhere a customized Linux OS is needed. Yocto is an open source project with many participants, including lots of companies and organizations, including the Linux Foundation. Let's go through some of Yocto's features. Yocto uses a layer model. What this means is that you can tailor your image however you want in a maintainable way. Each layer is more or less independent, and layers can be swapped out or added to extend the system, make customizations, and keep the codebase organized. A use case for this is a company that has several Linux products. What they can do is create a core Linux distribution which standardizes basic system components and configurations, and then you can augment this distribution with different features to produce a number of different images which reuse the same components. With Yocto, supporting different architectures such as Intel, ARM, MIPS, or PowerPC is achieved by including and using the corresponding board support layer. With Yocto, you can generate an SDK which can then be distributed to develop applications without the Yocto environment. Yocto provides a set of metadata which together forms Pokey, a reference and well-maintained embedded distribution which has a new release every 6 months. In this course, we will be using the THUD Pokey branch. There are many other features such as Eclipse integration, package management, caching, a web UI, and DevTool, all of which we will use in the future. Metadata is a key element of the Yocto project. You have three types of metadata: configuration files, which can hold global definitions of variables. These definitions tell BitBake what to build and what to put on an image. Recipes are the most common form of metadata. A recipe contains a group of settings and tasks for building packages. They describe where to get the source code and patches, dependencies, configurations, and compilation options. Installation instructions also get baked into packages. Layers isolate the information, be it by functionality or target architecture. Layers can define a board support package, which in Yocto is associated to the term machine, or they can hold a collection of related recipes used to build one or more packages. Pokey is an example worth exploring as a layer. For instance, Pokey is actually an integration layer which integrates the Open Embedded core layer and implements a reference embedded distribution in Yocto. There are also classes, which allow you to share information between recipes. This is a simplified architecture diagram of Yocto. In this case, for metadata, we have Pokey, the reference metadata, and third-party or even metadata you created. So BitBake takes this metadata, sorts the recipes in relation to their dependencies. It then generates a list of tasks to perform and executes them. The resulting products are package feeds, which can then be sourced to generate images or an SDK. Yocto leverages the Open Embedded project, specifically BitBake and the Open Embedded core collection of metadata, and provides additional tools, methods, and a collection of metadata which altogether forms Pokey, a reference embedded Linux distribution as we already mentioned. Adding new features with Yocto is easy, as there are many third-party layers. Let me showcase this by showing you the official website. As we can see, the latest release for Pokey is 2.6.1 thud. Actually, in the Git repository, it's already at 2.6.2. To see the officially supported layers, you can go to Software Overview, and here we have the officially supported layers, which are tested layers. And I should mention now that layers are always named meta dash and then a name. You could name them whatever you want, but this is the convention. So in this case, we see various layers. Meta Intel has some support for Intel platforms. Underneath the layer name, you have the release, Pokey release name. So this is compatible with Pyro, which is a version previous to thud. We have Meta Yocto BSP, which is actually part of Pokey, and so on for Texas Instruments. You also have a more extended list of recipes in the Open Embedded Layer Index, as we can see here. And these are separated, so you can search by layer, recipe, machine, which is BSP, classes, and in distros. As an example, you have a lot of layers here. Let's search, for instance, for Kodi, so you can easily integrate Kodi into your distribution. Recipes, let's search something like VLC. You have recipes for VLC and pretty much everything you can think of. Machines, let's search something like MIPS. So you already have a bunch of supported platforms. Classes, and probably a lot of distributions. Like this one was from Open Embedded. We can also take a glance at the official documentation, which is very complete. So you'll probably be spending a considerable amount of time looking at this documentation, which is low level, very specific. For instance, let me see if there's something interesting here in the table of contents. Managing layers, customizing layers using local.conf. So we will see what local.conf, where this file lives in the next chapter or so. But as you can see here, you can add a package to your image using this file, and you basically just need to add an entry similar to this line here. So what this does is basically append to this variable the utility strace, which is system call trace, and this would be installed then on your image. Let's look at something like machine. Okay, customizing the host name. So you can just basically specify this a value for this variable, and that will become your host name. Let's search more. This is what I was actually searching for. Okay, so this is an important variable. This specifies for which platform or which BSP you will build the image for. In our case, it will be the Raspberry Pi, or these are images that are officially already built in Pokey. So you have a bunch of QEMU compatible recipes, and for Edge router, which is a Intel, I think, platform router. So yeah, this is quite a high quality documentation, and I encourage you to read through it as you go through the exercises. Docker provides containerization around the application layer. What this does for us is to provide a consistent runtime environment across different platforms, thus aiding portability. That need arises often because software built under a certain environment often fails to run in another environment. This can be due to configurations or dependencies. For instance, an app might depend on a specific version of Python, or the C++ library versions between distributions are incompatible. A virtual machine can accomplish the same goals, but the overhead in terms of memory and CPU usage is greater than with containerization. If you want to support various applications, it quickly becomes unfeasible if you have to run multiple virtual machines to support each, especially on your workstation. In our case, since Yocto officially supports only a few versions of Linux, we use Docker, safeguarding your freedom to run the distribution you like the most, and we will be all working under the same environment. So if you face any issue, it's more likely that someone else has also had it, so it's easy to get help. In the next chapter, we'll build our first image, so let's go.